Okay, so today we'll be starting our new chapter. So this is our last chapter, wave optics. Okay, so after completing this, so if we get time, we will have a revision. Uh, okay, so under wave optics, we'll be having we have to study what is wave front. Okay, we'll start with wave front. What is wave front, and what is secondary disturbance and what is wavelet. So we'll start with that. Then what is Huygens principle. Then we have to explain the reflection and refraction of plane wave. Okay. So on the basis of Huygens principle or on the basis of wavefront that we have to discuss, we have to study. And we have certain proofs for laws of reflection. Okay. And also for laws of refraction using Huygens principle. Then we have to study what is interference. So Young's double slit experiment, how we have to do that to find what is fringe width and coherent sources. All these are the topics. Then we have to study what is diffraction. Okay, so diffraction, then polarization, and interference. So these are some of the new terms you will be studying under this chapter. Already under ray optics, you study what is reflection, what is refraction, right? What is reflection? What is refraction? Who can tell this the difference between reflection and refraction? Hmm? What is reflection and what is refraction? Reflection is something happening on the same media, right? When the light incident on a particular surface, it will reflect back on the same medium. And the laws of reflection says that the angle of incident will be equal to angle of reflection, right? Then the incident angle, the incident ray, reflected ray, and the normal all lies in a same plane. So this is the laws of reflection. So what is refraction? What is refraction? Refraction is what? When light travels from one medium to another medium. Okay, what will happen? The velocity of light changes, right? So the velocity of change, velocity since the velocity of the light or velocity of the wave changes, what will happen? This ray, when it comes from one medium and enters to the another medium, either it will bend away from the normal or bend towards the normal, right? So that this phenomenon we will call it as refraction. So what is the actual cause for refraction? What is the cause of refraction? Refraction. Anugraha. What is the cause of refraction?
Difference of speed in medium.
Yes, the light speed or the velocity of light is different. It's dependent on what the nature of the medium. If light travels from one medium to another medium, its velocity changes. So that is a root cause for refraction. Okay, so this thing you have to understand. Also, loss of refraction, like loss of reflection, we have loss of refraction also. What is loss of refraction says? Sine of angle of incident divided by sine of angle of refraction is equal to what? A constant. Mu. We call it as mu, right? Refractive index of second medium with respect to first medium. So that will be a constant, right? That is the first law of refraction. The second law of refraction, what it says? Second law of refraction. Refraction. What it says? എന്താ പറയണേ? Second law of refraction. Second law of reflection പോലെ second law of refraction what it says എന്താ പറയുന്നത്? Tell me രണ്ടായിട്ടൊന്നും പറ്റില്ല കേട്ടോ കൃഷ്ണ.
Incident ray, refracted ray,
Hmm.
and normal lies in the same plane.
Yes, refractor incident ray, refractor ray and the normal lies in the same plane, right? So that is laws of refraction, like laws of reflection. Second law of reflection പോലെ തന്നെ second law of refraction. So these things you have to Now, let me start. So, before going to in depth for this chapter, wavelet and wavefront, so you have to understand the nature of light. So, what is the nature of light? So, under the dual nature of matter and dual nature of radiation, we studied that light or like having what? It's having a wave nature, also having a particle nature, right? What wave nature says it's move like a wave like this. Particle nature says that light is made up of particles that is called photons, right? So two nature of light. One is wave nature and one is particle nature. So these phenomena, how many phenomenons? Five phenomenons. Starting from reflection, you know that. Refraction, you know that. Diffraction, that you are going to study. Interference, polarization. These five phenomena of a light is going to explain based on the wave nature of light. It's not possible to explain these phenomena based on particle nature. Using particle nature, we can explain this phenomenon, photoelectric effect. You would have been studied under dual nature of particle, right? Photoelectric effect. What is photoelectric? So, these are two nature, wave nature and particle nature. So, these five phenomena, reflection, refraction, diffraction, interference, polarization. These phenomena we can explain based on wave nature. But the photoelectric effect can be explained only using particle. Clear? Clear? So what is photoelectric effect? What is photoelectric effect? Aditya, what is photoelectric effect? What is photoelectric effect? Photoelectric. From the name itself, you can say. What is photoelectric effect? Niranjana, what is photoelectric effect?
Emission of photon when light of certain frequency falls on a surface.
Is it emission of photons? Photons is light, right? It's light incident on a photosensitive material. That is photon incident on a light sensitive material. What is emitting? Electrons are emitting or photoelectrons. That phenomenon is called photoelectric effect. So that there we are explaining that photoelectric effect. We already explained under the chapter 11 photoelectric effect is with the help of particle nature. Right? Okay. So reflection, refraction, diffraction, interference, and polarization based on wave nature, and photoelectric effect based on particle nature. So we have studied lot of theories. Most of the theories you already studied in your school classes, and some of the theories you studied in your 12th standard. Okay, based on these available theories, corpuscular wave theory, EMW theory, Planck's quantum theory, we have explained the nature of the light, either the wave nature or the particle nature. Okay, can you tell me which theory explains the particle nature? We have four theories here. Which theory explains the particle nature? Which theory explains particle nature? Tell me, fast, fast, quick. Particle nature, Planck's quantum theory, right? Planck's quantum theory explains the particle nature. It says that wave is consisting of particles called as photons. Corpuscular theory. What is corpuscular theory? You would have been studied what reflection of light, right? So there you are saying that light is moving in a straight line in the form of rays, right? In the form of rays. So corpuscular theory says that its light is made up of tiny particles, which is called corpuscles. Tiny particles, small particles. And it's also stated that light propagate in a straight line. When you study ray optics, you already drawing the ray of light in a straight line, right? So that is based on corpuscular theory. Right? Incident ray, reflected ray, refracted ray, all these rays you will be drawing. It's a straight line. So that concept was corpuscular theory. But light is not moving in a straight line. That is the real scenario. Light is a what? It's a wave in nature. Okay, even though it's have photon characteristics also, but we can say that it is moving in a wave kind of movement. The corpuscular theory states that it is made up of tiny particles called as corpuscles and light propagate in a straight line. Wave theory, who invented Huygens and Fresnel and Young. Experiment, different experiment we have to study under this chapter. Huygens was saying that wave is a longitudinal wave or wave theory or light is a longitudinal wave. Fresnel and Young explains wave as a transverse wave. What is the difference? Longitudinal wave and transverse wave. Wave is moving like this. If you put a stone in a water, there will be waves of water, right? So if the waves is moving, the particles in on the water will move up and down, right? Is it a kind of what type of wave? Longitudinal or transverse? These are these are transverse wave. That means if the particle in the medium is oscillating perpendicular to the direction of propagation. Wave is moving like this, but the particle is propagating perpendicular to that. So that is transverse kind of wave. If particles are vibrating, if waves are moving in a medium, in that case, if particles are vibrating horizontally, like this, horizontally, that kind of wave we will call it as what? Longitudinal. Can you tell me one example for longitudinal wave?
EMA,
Which wave?
electromagnetic wave,
Electromagnetic wave is a longitudinal wave. No. Sound wave, right? Sound wave. How it is like it will when I'm speaking, my voice is traveling in that way. Like it's compressing the nearby air, right? It will compress, then again decompress, compress. So that way, in that scenario, when the sound wave propagate, that particle in the medium or in the air will oscillate horizontally like this. Sound wave will be moving like this. So the direction, when compared to the direction, these particles in the medium will oscillate like this horizontally. So that is an example of longitudinal wave. EM wave, why it is electromagnetic wave, electric and magnetic. Their oscillation is perpendicular. Their transverse nature of electromagnetic wave. പഠിച്ചിട്ടില്ലേ മറന്നുപോയോ? EM waves are transverse in nature. Their oscillation is happening perpendicular to the direction of propagation. The electromagnetic wave, electric field and magnetic field oscillating perpendicular to the direction of propagation, right? So that's why that EM wave is a transverse in nature. Okay, clear? It's a very basic concept, should be clear. What is transverse wave? What is longitudinal wave? Any doubt on this? Just compare two things. Visualize that. Water wave, where stone pushes. There, particles are oscillating horizontally. Example, foot transverse wave. Sound wave, particles in the medium oscillating horizontally. That is longitudinal. Okay? EM waves are explained by Maxwell that transverse. E and B field oscillate transverse in nature. Planck's quantum theory says that light is made up of small packets of energy, which is having quantum of energy. We call that packets as what? What we will call? We will call it as. എന്താ പറയാ നിങ്ങളെല്ലാം ഉറങ്ങാണ് എല്ലാരും ജോയിൻ ചെയ്തേ. Hmm?
Photon.
Photons. We will call it as photons. So these are the different theories that explain nature of light. So should understand what this theory, like each theory, what it states. Okay, there is a chance of a question like they will give some statement. So is the statement is correct according to corpuscular theory? They can ask in assertion type question, right? So you should understand what exactly theory states. Okay, so these different theory and these statements should be clear. These statements giving what each theory states and who is a scientist related to that. For corpuscular theory, I forgot the scientist name. I think it is Isaac Newton. One more scientist was there. I forgot his name. Wave theory, Huygens, Fresnel, Young, Maxwell, EM wave, Planck, from the name itself. Now, we will move to important part of this job. Very, very basic thing. If you are not understood what is wavefront, if you not understood what is ray, if you not understood what is secondary disturbance, if you not understood what is wavelet, will not able to understand anything from this chapter. Okay, should understand what is wavefront. So I'm going to explain what is wavefront. Listen carefully, understand it. Okay, in today's class, I will explain what is wavefront, what is wavelet, Huygens principle, and Huygens construction of primary and secondary wavefront. So these topics I am going to explain this today class. Okay, so should be very clear. Understand it today itself. If you have any doubts, please feel free to ask. What is a wavefront? This is a definition. Read this definition. You will not able to understand anything. It is defined as the continuous locus. Continuous locus. It is defined as the continuous locus of all such points of the medium which are vibrating in the same phase at any instant. മനസ്സിലായോ? ഒന്നും മനസ്സിലാവില്ല. Now, see this. Take this example. What is this? I'm just dropping a stone in water. So these waves will produce, right? What is the nature of this wave? It's a transverse or longitudinal?
Transverse.
Transverse, right? Because the particles oscillate. See, here if it is a particle in the water, suppose I am putting a leaf here, the waves will travel like this, but the leaf will move up and down, up and down. So leaf is a particle. So this is a transverse in nature. Now you think that there is lot of particles for this particular section. There is a circle, right? You can see one circle is formed like this. So there will be lot of particles. Tell me, this is one circle I am taking and another circle. Let me draw two circles. One circle I am drawing here over this portion. Okay. So just connecting all the particles at this point. Another circle I am drawing here. The both are in different. Okay. Not good. Whether don't draw. So you can see two like one. This is upper, right? This in like that particles will be in the upper portion, right? Those particles here will be in the upper, but those particle here will be the down, right? So all the particles here, we can say that in a position with high altitude or anything, high energy, or simply I can state in a same state of energy. Simply, or simply I can say it is in the same state. all the particles in this portion of this wave are in the same state. Similarly, all the particles in this കുഴിഞ്ഞൊരു ഭാഗം കാണുന്നില്ലേ അവിടെയുള്ളതും will be in same state, but the state of this and state of this will be different, or the energy of this and this will be different. Okay, so if I draw a circle joining all the particles like here, this will, and we can call it as, this is a continuous locus. This circle joining all the particles on the upper motion, this is a locus. Similarly, this is another locus with a different state of energy. So these locuses are called wavefront. What? Wavefront. So the state, we can say, I told that it's the same state, right? So the same state, we can say that with the term, physical term, phase. Same energy, same position, same state simply. So that same state in physics, we are taking term phase. All the particles the same phase. Now you read the statement. Wavefront is defined as the continuous locus of all such points of the medium which are vibrating in the same phase at an instant. Still not clear? Then we will see one video, then it will be clear. We show one video. Without understanding wavefront, we should not move to the next topic.
Newton proposed
If not understood, please ask. Okay.
that light is made up of particles.
Is it audible?
When you're looking at a bulb, for example, you would imagine, the proposed light is made up of
സാറിന്റെ ബോഡി ഓഫ് ചെയ്താൽ മതി.
imagine, there were no bulbs back then, but if there was, then you would imagine bullets coming.
Yes.
Sir.
Newton proposed that light is made up of particles. So when you're looking at a bulb, for example, you would imagine, there were no bulbs back then, but if there was, then you would imagine bullets coming out of these bulbs, and that's what light was, particles. He called them corpuscles. On the other hand, a Dutch physicist named Christian Huygens, and that's not how you pronounce his name. Turns out that his name is pronounced somewhat like Huygens or something like that. But I'm just going to go ahead and call him Huygens. He proposed that maybe light is not particles, but instead light is made of waves, very similar to the waves in water. And I want to explore, the goal of this video is to explore this wave nature of light. So one question we could be having is, when it comes to water particles or waves in water, the water particles are the ones that are doing the vibrations, right? When you disturb, when you disturb still water, then the disturbance is carried away by the vibrating water molecules. But in light, what particles are vibrating? That's a question that you can immediately ask Huygens, because he's claiming light to be a wave. Well, back then, Huygens and a bunch of other folks assumed that there are particles everywhere in the universe, and this medium which consists of these particles, they called it the ether medium. This was a very popular notion back then. Ether medium. They assumed that this medium was everywhere. Sort of like air, you can't see it, but you can't even feel it, but it's there. That's what they said. Okay? And Huygen says that light is vibration. Light is, light waves are carried by the vibrations of the ether medium. So light is propagated by the vibrations of the ether medium. Now, if you want to visualize something like that, here's our animation. Here's a light bulb, and these particles are the particles of the ether medium that's present everywhere in the universe. And this is how Huygens imagined it. Light is basically disturbance propagated by the vibrations of the ether particle. Ripples. Light is ripples in the ether medium. Beautiful, right? Well, now there's one difference, big difference between the ripples of light and water. These waves are on the surface two dimensions. And so these ripples are interstellar. You have seen them. But light is a wave in 3 dimensions. So you can't see this in three dimensions. So these ripples are not circles, but spherical ripples. That's a major difference that you're finding. So this is a 3D wave. But now we're going to ask a question. We can ask, what exactly are these ripples? Whether you consider light or whether you consider water, what exactly are those ripples? So let me get rid of that. So what exactly is ripples? Well, in physics, these ripples have a very, very technical, fancy name. We call them wavefronts. And you'll keep hearing this word over and over again in the future videos. So let's clarify what these wavefronts are. Well, wavefronts, let me just define them first and I'll show you. Wavefronts are basically set of particles which are in sync with each other, which are vibrating in sync. And again, there is a technical term for particles vibrating in sync with each other. We call them in phase with each other. We just need to familiarize ourselves with these technical terms. So what do I mean by this? Well, if I come over here and look at one of these ripples or wavefronts and concentrate just on them, what I will find now is that every particle on that ripple or on that wavefront is at the topmost position. And that's why that ripple is a crest. A little later in time, you'll find all those particles will be at the bottommost position, forming a trough. Let me show you one more, which is already a trough over here. We usually denote trough by dotted lines. A trough, if I look at that particular ripple, then you'll find all the particles on that are at their bottommost position. The important thing to note is that all the particles on these circles, they are always vibrating in sync with each other. They're vibrating together, in phase with each other. Such a set of particles is what we call a wavefront. And the same would be true for all light as well. Again, let me bring back that visualization. If I were to concentrate on one of those spheres and just look at those spheres, what you're finding now is, look, all the particles on that spheres are vibrating in sync with each other. You see that? Look at it one more time. All right, there you go. Look at that. They are vibrating in sync with each other. Such a set of particles which are vibrating in sync with each other are what we call wavefronts. The last question I want to explore is, what in general would be the shape of these wavefronts? Well, think about water first. If you were to disturb it at only one place, at just one tiny spot, then you'll get these nice circular ripples or circular wavefronts. But if you were to disturb this all around with your hand everywhere, then the wavefronts are going to be all messed up and will have weird shapes, right? Same would be the case with light as well. Again, looking at that animation, if the light source that we're dealing with is pretty tiny, or we're looking a little bit far away so that the bulb appears tiny, then the wavefronts are going to be spherical in nature, just like those ripples. But if you were to have a big source, or if you were to go very close to that light bulb, where you can no longer neglect the size, now very close to that light bulb, the wavefronts won't be spherical. They might have different shapes depending upon the shape or the size of this light source. But if you go far away, a little bit far away, where it appears to be a point, then the shape is going to become spherical. But I want you now to pause this video and think a little bit about what would be the shape of the wavefront if you were to go really, really far away from this light bulb. Think about that. That sphere is going to become really, really.
Is it clear? What is wavefront?
Yes.
Yeah, clear to all of you.
Yes.
These white circles drawn are wavefront. So that we will call it as a continuous locus. So in the case of a water wave, it is two-dimensional circle. Okay, the locus was two-dimensional and it was a circle. But when I am having a point source like this, kept in air, so the wavefront, the wave will propagate spherical, three-dimensional propagation. So in that case, what is the wavefront? Is it in circular or spherical? When the source is point source, three-dimensional, so the wavefront will be spherical in nature. Spherical in nature. Okay, so you can see this video also, right? There are a lot of dotted lines. So these dotted lines, we can say that it's a medium or it's a particle of the medium, and the energy is propagating from this source to longer distance. So these particles, the yellow particles, are oscillating or vibrating. So the vibration, some of the particles, the vibrations are identical. If we draw a line, if I draw a line joining all these particles which is having the same vibration, then that line will give a wavefront. That line will give a wavefront. In the case of water wave, it is a circle. But in the case of a point source like bulb, small bulb, it will radiate or it will wave will move three-dimensional, right? So if you say that, this will be a spherical in nature. Okay, so at a particular distance of radius r, let it be capital R, all the particles in that sphere will vibrate in the same way. So if you draw a line here, not a line, so here it is a three-dimensional spherical shape I have to draw. So that will give the spherical wavefront. Got it? So let me ask one question. Suppose my point source or my source is rectangular in shape. My source of light is rectangular in shape, like a tube light kept perpendicular to the earth. Then what will be the shape of the wavefront? This is also three-dimensional, right? What will be the shape? If I am using a rectangular shape source, what will be the shape of the wavefront? What will be the shape of the wavefront? It will be cylindrical in shape. It will be cylindrical in shape. If I kept a point light source, then the wavefront is spherical in nature. But if I kept a rectangular source, rectangular light source, then its wavefront will be spherical in nature. Spherical in nature. Got it? What is spherical wavefront? What is cylindrical wavefront? Is it clear? Clear?
Yes.
Now you tell me what is plane wavefront. Suppose, see, this is a spherical wavefront, right? In this picture, light source, three-dimensional. So if you see a wavefront very far from this light source, let it be here. Let it be here. Another one, like again, too far. So if you see that, it will be bigger sphere, like bigger sphere. So if we stand near to that sphere, we will see that it is a kind of a, we will see, we cannot identify that it's a big sphere. We can see it is a plane like this, right? Like our earth. Earth is spherical in nature, right? ഭൂമി ഉരുണ്ടതാണ്. പക്ഷെ നമ്മുടെ എർത്തിന്റെ സർഫേസിൽ നിൽക്കുമ്പോൾ നമുക്ക് ഉരുണ്ടതാണെന്ന് തോന്നുന്നു. ഇറ്റ് ഈസ് എ പ്ലെയിൻ ഇൻ നേച്ചർ അല്ലെ, പരന്ന ഭൂമിയാണെന്നുള്ള എർത്ത് നമ്മൾ പരന്ന ഷേപ്പ് പ്ലെയിൻ ആണെന്ന് തോന്നുന്നു അല്ലെ. പക്ഷെ ആക്ച്വലി ഇറ്റ് ഈസ് സ്ഫിറിക്കൽ ആണ്. പക്ഷെ വളരെ വലിയ സ്ഫിയർ ആയതുകൊണ്ട് നമുക്കത് അതിന്റെ അടുത്ത് ഒരു പോയിന്റിൽ പോയി നിൽക്കുമ്പോൾ നമ്മൾ വിൽ ഫീൽ ദാറ്റ് ഇറ്റ് ഈസ് എ plane in nature. Same way, spherical wavefront or the cylindrical wavefront with bigger, longer distance from the source will looks like a plane wavefront. Plane wavefront. So, the plane wavefront are those wavefront which is part of spherical and cylindrical when we looks very far from the source of the light. Yeah, let me show. So, is defined wavefront, no doubt അല്ലേ. ക്രസ്റ്റിലുള്ള എല്ലാ പോയിന്റും ജോയിൻ ചെയ്ത് ലൈൻ സർക്കിൾ വരച്ചു കഴിഞ്ഞു കഴിഞ്ഞാൽ ദാറ്റ് ഈസ് എ ലോക്കസ്. ദാറ്റ് ലോക്കസ് വിൽ കോൾ ഇറ്റ് as one wavefront, and this is another wavefront, another circle which is in same piece. Only thing is the vibration ഒരേപോലെ ആയിരിക്കണം പാർട്ടിക്കിൾ ജോയിൻ ചെയ്യുക, that's it, then we'll get a wavefront. If the wavefront we can classify into spherical, cylindrical and plane. If the source is a point source, then the radiation will be three-dimensional. Then the nature of the wavefront is spherical in nature. If the source is, this is a source, okay, rectangular source in the center, you can see, right? So then the source, if the source is rectangular in shape like this, then the wavefront is what? Cylindrical wavefront. Plane wavefront is nothing but it's a part of spherical and cylindrical wavefront. These are part of spherical and cylindrical wavefront when we look far away from the source. എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ ഇപ്പൊ ക്ലിയർ ചെയ്യാം. What is wavefront? What is spherical wavefront? What is cylindrical wavefront? What is plane wavefront? No doubt, right?
Plane wavefront ഒന്നും പറയാം.
Yes. See, എർത്ത് നമുക്ക് എങ്ങനെ പ്ലെയിൻ ആയിട്ട് തോന്നുന്നത്? How we can say that? See, നമുക്കറിയാം എർത്ത് സ്പിരിക്കൽ ഇൻ നേച്ചർ ആണ് അല്ലേ. പക്ഷെ നമ്മൾ ഇവിടെ നിന്ന് നോക്കുമ്പോൾ നമുക്ക് സ്പിരിക്കൽ നേച്ചർ ആണെന്ന് മനസ്സിലാവോ? പ്ലെയിൻ ആയിട്ടില്ല തോന്നാ. സെയിം വേ നമ്മൾ ലൈറ്റിന്റെ സോഴ്സ് ഉണ്ട്, വലിയ എർത്തിന്റെ അത്ര റേഡിയസ് ഉള്ള ഒരു സ്പിരിക്കൽ വേവ് ഫ്രണ്ട് ഉണ്ട് എന്ന് വിചാരിച്ചോ. ലോങ് ഡിസ്റ്റൻസ് ഫ്രം ദ സോഴ്സ്. ആ വേവ് ഫ്രണ്ടിന്റെ അടുത്ത് പോയി ഞാൻ നിന്ന് കഴിഞ്ഞു കഴിഞ്ഞാൽ എനിക്കത് എന്തായിട്ടാ തോന്നുക? സ്പിരിക്കൽ ആയിട്ട് തോന്നുമോ? ലൈക്ക് നമ്മൾ എർത്ത് കാണുന്ന പോലെ തോന്നുമോ? പ്ലെയിൻ ആയിട്ട് തോന്നും അല്ലേ? അല്ലേ? പ്ലെയിൻ ആയിട്ടില്ല തോന്നാ. സെയിം തിങ്. So plane wavefront is a part of spherical wavefront or cylindrical wavefront when we looks the wavefront very far away from the source. Clear? Clear?
Yes.
Anugraha? Aditya?
Yes, sir.
Clear.
Yes.
Vaishna?
Yes, sir.
Clear. Ranjana? ഇത് മനസ്സിലായില്ലേ? ഒന്നും മനസ്സിലാവില്ല നീ പറയുന്നത്. അവിടെ എത്ര ടൈം സ്പെൻഡ് ചെയ്ത. Now, what is ray of light? Plane wavefront undo, spherical wavefront. So those lines drawn perpendicular to the wavefront. Those lines drawn perpendicular to the wavefront. You can see the red line, right? So these here also red line, here also red line. So whatever be the wavefront shape, cylindrical or spherical or plane, the lines be drawn perpendicular to that wavefront. We'll call it as very very important concept. This we required when we derive reflection, refraction, law of reflection, law of refraction based on Huygens principle. നമ്മൾ derive ചെയ്യുമ്പോൾ ഈ ഒറ്റ കോൺസെപ്റ്റിലാണ് ആ derivation complete. So should be in your mind. The rays are perpendicular to the wavefront. So rays are the straight line drawn perpendicular to the wavefront. This group of parallel rays, more than one rays parallel ആയിട്ടുള്ള rays combine ചെയ്തിട്ട് we will call it as beam of light. Ray of light, then beam of light. Okay. Now we will move to Huygens principle. What Huygens says? What is Huygens principle? സ്കൂൾ പഠിച്ചതല്ലേ? പറഞ്ഞ നോക്കട്ടെ. What is Huygens principle says?
All point on the primary wavefront act as a source for secondary wavelets and send secondary wavelet in all direction, similar to original points.
What is wavelet? Eh? So according principle correct ആണ്. According to this principle, each point on a wavefront is a source of secondary waves which add up to give the wavefront at any later time. That means if you see spherical wavefront or cylindrical wavefront, so I'm taking the cylindrical wavefront for example. Each point on this cylindrical wavefront, any wavefront, okay, I'm just for explaining, I'm taking cylindrical. Each point on this cylindrical wavefront act as a source for secondary disturbance. Okay, and these secondary disturbance we will call it as wavelet. We will call it as wavelet. Okay, and we can find out this or by joining the tangent. If I am drawing a tangent to this wavelet, secondary wavelet, we will get the secondary wave. I will explain it. I will show video, then it will be more clear. Just reading the principle again. According to this principle, each point on a wavefront is a source of secondary waves which add up to give the wavefront at any later time. So we will see this video, then we will get more idea. We see this video, then we will explain this picture. In your textbook, this picture is there. Nothing you will get understand by seeing this picture. So I will just first I will show this video, then you will get to understand the concept.
If you shine a parallel rays of cardboard with a tiny hole in between.
Voice
Yes.
ഞാൻ മ്യൂട്ട് ചെയ്യാണ് ഉള്ളത്.
you see that it has, but which lays of